Hey, pre-cal kids, today we're looking at vectors, section 8.2, looking at, sorry, 8.1, looking at vectors. Notes out, and away we go. Now we've looked at vectors in trig, and if you're in physics, you've also looked at vectors. So this will be a good chance to kind of review those topics. Remind me in class, and we'll watch this video, this short video on vectors. What is a vector? A vector is a quantity that has both magnitude and direction. A lot of physics applications are vectors. For example, if I say 3 feet, 3 feet is not a vector because there's no direction. But if I say 3 feet north or 3 feet east or 3 feet up, that gives it a direction and turns that magnitude into a vector. So quantity that has both magnitude and direction. Examples of vectors are velocity, acceleration, and force. There are others. Every vector has an initial point. So here's our initial point, P, and our terminal point, the ending terminal, point Q. And we use an arrow to show the direction going from P to Q. For vectors, we're going to use a symbol. For example, this is vector A. So the symbol we're going to use is, like if I want to say vector X, it's kind of a little half arrow above X. That's going to be our vector symbol. We could also call this is vector A. This would be the same thing as vector PQ, just like a line segment. We can use the initial point and terminal point with the arrow always on the terminal point. That will work for vectors. We can find then the magnitude, or we'll talk about that in a second. What is the magnitude? The magnitude is simply the length of the vector. So the length of the vector is denoted by, we're going to use the absolute values. Now this is not absolute value, but we're going to use the absolute value symbols to denote magnitude. So again, for our vector, that would be the magnitude of vector A. Again, we can use the endpoints to name that, the magnitude of vector PQ. Just like in trig, we're going to define standard position vector as a vector with its initial point on the origin. Remember, for any vector, we can drop in an XY coordinate plane to establish any vector at the origin. The direction, just like in trig, the direction is the angle between the positive x-axis and the vector. We're always going to go from the x-axis. That way we don't have to worry about if we're coming from the y-axis. We can also define then a zero vector. A zero vector is a vector with the same initial point and the same terminal point, and that is at the origin. It's denoted by the vector 0, so the zero vector. Doesn't really do much. It has to do with the rules of vector properties and stuff. Equal vectors, well, what would make it a vector equal? Vectors are equal if and only if they have the same direction and the same magnitude. Both parts have to be true. And so let's put that to work. Checkpoint 1. Use a ruler and a protractor to determine the magnitude in centimeter and the direction of vector n. So we want first the magnitude. Magnitude of vector n is the vector in absolute value bars. And we're going to use our good old ruler in centimeters. This is about 3.3. So there's our magnitude. To get direction, we're going to call that theta. We need a coordinate plane. How are we going to get a coordinate plane? Well, we're simply going to drop in an x and y axis. And then we're going to use a protractor. And we should get something that goes, let's see what we get here. Now, part of this is going to depend on where your axis is. So here I get about 35 degrees. And I know I can just do 35 degrees because we're going to assume that that comes from the north, from the x-axis. Second part, giving these vectors, let's identify what we know about them. Are they the same or not the same, and why? So let's look at vector z and vector y. What do we notice about vector y and vector z? Well, they have the same magnitude because they're the same length, and they're going in the same direction. So these are equal vectors. Again, how do we know that? Because they have the same magnitude and direction. Same magnitude and direction. What about vector v and vector u? Vector v is here, vector u is here. Well, they look to be the same length. They're both going downward. So again, they are equal vectors. Again, for the same reason. They have the same magnitude and the same direction. So I get x and w. Well, here's x. Here's w. Well, they're going the same direction, but are they the same length? They are not. So these are not equal. Y, they have the same direction, but different magnitudes. And let's look at the last two, vector v and vector y. Vector v is going down, vector y is going up to the right. So they have different directions, but what do you notice? They are the same length. So they're not equal because both has to be true. They have the same magnitude, but different directions, which I'm going to abbreviate as theta. When we put two or more vectors together, we're going to call that the resultant. That's usually going to be our answer in a physics or a trig problem. That's the resultant vector. There are two methods that we can use to get the resultant vector, and that's the parallelogram method and the triangle method. Really, they're the same. It's just how much work do you want to do for each problem, and it depends on the problem. Usually, triangle method's the easiest to do. Sometimes the parallelogram method works just as well. And we'll illustrate, we did that in trig last semester, so we'll review that here. Number two, find the sum of vector v and vector w using these two vectors. A, let's use the parallelogram method. So what does that mean? Well, that means we're going to start with our vector v. So there's my vector v. And from the same initial point, I'm going to use vector w. So there's vector v and vector w using the same initial point. Then what I'm going to do is I'm going to create a parallelogram from the terminal point of vector v. I'm going to sketch the same vector w. And from the terminal point of w, I'm going to sketch the same vector v so that the opposite sides are parallel, thereby giving me a parallelogram. The resultant vector then has to be from the initial point of v and w to the terminal point of v and w. And there's my resultant vector called vector r. And again, I should note on the previous that the resultant vector is what we'll usually call the r vector. Usually we'll save that r to be the r vector. So that's the parallelogram method. The triangle method is kind of just a shortcut of that. So if I pick either vector, it doesn't matter which one I pick, I'm going to pick here vector v. So there's my vector v. And I just used that one, and from that terminal point, I pick vector w. Then that's really just half of my parallelogram, and then the resultant is the resultant vector. So depending on how you draw your picture, sometimes each method has the same, and then see what you notice, they're the same. We get the same vector either way. This is what Mrs. Goebel, the triangle method is what Ms. Goebel calls the tip to tail method. It's really the triangle method. How can we use that in our problems? Example 3, you refer to the application at the beginning of the lesson. At the European Championships, a sailed plane traveled forward at 8 meters per second and descended at 4 meters per second. So we're going to set up a XY coordinate plane where we're going to assume this way is forward. And we know the sailplane is going forward at 8 meters per second. While it's going forward, it's also descending. Gravity is pulling it back down to the earth at 4 meters per second. That gives a resultant path of the plane at the vector r vector. Question, determine the magnitude of the resultant velocity of the sailplane. Well, what are we going to do here? Well, there's a right triangle. We know two sides. We want to find the hypotenuse. That is just classic Pythagorean theorem. So the r vector magnitude is equal to, and I'm going to come up with a formula for this, the x direction. So that would, for lack of simplicity, the x vector squared plus the y vector squared square root. So just Pythagorean theorem. So that means the r vector is going to equal 8 squared plus 4 squared square root, and we'll plug that in our calculator, and that means the resultant vector is 8.94 meters per second. We can also then define opposite vectors, just like opposite numbers, they have different signs, same thing. Opposite vectors are two vectors that have the same magnitude, but are going in opposite directions. For example, if this is vector g, the negative vector g has to be going the other direction. Here's vector h. Negative vector h has to be going in the opposite direction, and vice versa. We also then define a scalar. We saw this when we did matrices, because we can actually turn any vector into a matrix, which we're not going to get into, but we can still use scalars. A scalar quantity is a quantity with only magnitude, no directions. For example, mass, length, time, and temperature are all magnitudes, no directions. Those are scalars. We can use a scalar then as the number used to measure scalar quantities. So we can apply scalars to vectors, and here we're just going to look at the picture. Use the triangle method to find the resultant vector. Again, we're going to just always assume that this is going to be the resultant vector r. Our book doesn't define it that way, but that's how we're going to use this in the problem. So this will just kind of make more sense. How are we going to do that? I'm going to go out here to the side where I have a little bit more room. I want two vector v's. So 2 times v means I need 2 vector v's. So here's 1 vector v. Here's 2 vector v's. So this whole thing has to be 2 vector v's, right? To get 2 vector v's, I just draw 2 vector v's. Now I want half of w. So here's whole w. I want half of w. So here's 1/2 of w. But I want to subtract it. Well, how am I going to subtract a vector? Well, we're going to go back and do the opposite, because negative means we're just going in the opposite direction. So here, instead of going up to the right, we're going to come back down to the left. So there's my negative 1/2 w. Again, we're going to use our triangle method, and I'm just going to draw the same picture. There's my negative 1/2 w. And then the answer is our resultant vector, and that's the vector that started at the original point and meets that w. So there's our vector r. So that picture would be your solution. Again, we need to practice those pictures because that's what we're going to use when we start solving problems. We can also then define parallel vectors. Parallel vectors are the vectors that are parallel if and only have the same or opposite direction, or they have to have the same theta. Then they're parallel. Component vectors are the 2 vectors whose sum is a given vector. So here, for example, vector p and vector q are making vector x. Vector p and vector q would be the components. On the first part, we would say then the vector I is parallel to vector J. Vector L is parallel to vector K. Again, note they don't have to be going in the same direction to be parallel. And finally, let's look at two applications. These will work kind of like trig problems or kind of like physics problems. We're just going to draw a picture and then do the math. A ship leaving port sails for 75 miles in a direction 35 degrees north of due east. So we want 35 degrees north of due east. It's a little bit bigger than a 30, less than a 45. So there's our 35 degrees. And it went for 75 miles. So this is actually our resultant vector. Our question then is find the magnitude of the vertical and horizontal components. What does that mean? Well, that means we want to find the y vector and we want to find the x vector. How are we going to do that? Well, that's good old trig, right? X is adjacent, y is opposite. That means we're going to use sine and cosine. Good old sine and cosine. So what do we know? The sine of 75 is equal to our vector x over the hypotenuse, right? That's just the definition of sine. And therefore we get our formula. The x vector will actually always be the resultant. X is always the resultant vector times the sine of theta. Y then is always the resultant vector times cosine of theta. And we'll see that play out throughout the rest of this chapter as well. So that gives us x is equal to 75 sine of 35. That should be a 3. And we'll punch that in our calculator. And if we punch that in our calculator, we should get the x component vector is 61.4 miles. Same thing for the y vector then is opposite opposite over hypotenuse. I feel like I didn't do that right. That should have been cosine, sorry. X is cosine. Sine is opposite, cosine is adjacent. So now we want y is opposite, so that is sine. So vector y is our 75 times cosine of 35, and we'll plug that in our calculator, and that is 43.0 miles. Sometimes we can write that as a component vector. We'll actually get to that later. So the x would be 61.4 miles, 61.4 comma 43.0. So we're writing that in component form. We'll get to that tomorrow in the next video, I believe. And number 6, 2 parts. A piling for a high-rise building, that's like a concrete foundation, is pushed by 2 boulders exactly at the same time. One boulder exerts a force of this in a westerly direction, so we need our coordinate plane. So in a westerly direction, so I'm going to draw a random arrow west. Again, this is north, south, east, west, if you're not good with directions. And that was 1550. And the other bulldozer pushes the piling with a force of 3050 in a northerly direction. You can either use the parallelogram method and put that north on the north axis and then draw the diagonal, or you can go tip to tail. So there's our northerly, and that was 3050. And so we want what is the resultant vector. There's our resultant vector, both the magnitude for part A and then the direction for part B. Well, how are we going to do that? Well, the magnitude is simply Pythagorean theorem. So that's our r vector squared is equal to 1550 squared plus 3050 squared. And if we square root both sides, then we should get about 3,420 pounds of force. In what direction? That's part B. We call then for part B to find theta, that's our angle, theta is equal to the tangent inverse of the y vector over the x vector. Rise over run. And so that's tangent inverse of 3050 over 1550. But here we have to remember something about trig. Is 1550 going to the right? It's not. It's going to the left, so that has to be a negative. And we're going to put that in our calculator, and you should get about 63 degrees. And so what's our answer? What is the direction of the resultant force? So we can either answer 63 degrees north of west, or we could come back with the complementary angle, which would be 27 degrees west of north. Typically, we want to use the first one, so we're always going from the x-axis, not the y-axis. Homework set, page 491, 14 through 17, 18 through 28 evens, 31 through 35, 40, 50 through 52, 8-1 vectors. Have a good day, kids.